We now have a respectable understanding of the periodic table itself and the atoms in them. And now we're ready to deal with molecules themselves. And to deal with molecules, we have to have some way of representing them, and you represent them with formulas. And there's actually three major ways to represent a molecule. One is the molecular formula. Molecular formula. And the other is the empirical formula, and I'll do it in a different color to differentiate it. Empirical formula. And the difference is, well, let's just talk about what the word empirical means. I remember when I first took chemistry, the teacher kept using the word empirical. I was like, well, what does empirical really mean? And I clearly did not have a very deep vocabulary. I forgot what age it was. But it means achieved through observation or experiment or based on experience. So if someone says that they empirically figured out X, Y, or Z, it means that they figured it out through an experiment or they observed it. The molecular formula is essentially the actual number of atoms in that molecule. Let me show you what I'm talking about. So the empirical formula tells you what people have observed, maybe before they even knew that there was such a thing as atoms. What they would have observed is the ratio of the atoms to one another in a molecule without knowing in the exact molecule how many of that atom there are. Let me show you what I'm talking about. So if I were to give you, I don't know, a benzene. The molecular formula of benzene, you have 6 carbon atoms and you have 6 hydrogen atoms. Now, if you were, some chemist in the 1800s and you didn't know about the actual atoms, but if you had a big bag of benzene and you were to measure the ratio of the carbon to the hydrogen that you had in that bag, you would find out that for every 1 carbon, you have 1 hydrogen. So your empirical formula is the ratio of the two. You don't know that each atom actually has 6 of these, but you know that for every carbon, there's a hydrogen. For every hydrogen, there's a carbon. And the way to go back, you can go from the molecular formula to the empirical formula very easily. You just find the greatest common divisor of the number of atoms in the molecule. So the greatest common divisor of 6 and 6 is obviously 6. You divide both of these by 6, and you get the empirical formula. It's not easy, or you pretty much can't go back from the empirical formula to the molecular formula. You've lost information. I don't know whether this was C6H6, was it C2H2. You just don't know. And I mentioned right at the beginning of the video that there's a third way to represent molecules, and that's the structural formula. And we'll do that off and on, and we've already done it a little bit. Let me show you. The structural formula for benzene would actually say how the molecular formula atoms are configured. So benzene in particular, it's a very interesting, it looks like this. It's often drawn like this, and you'll see this a lot when you take organic chemistry. But it looks like a little hexagon where the vertices of the hexagon are carbon atoms. So let me draw the carbon atoms in yellow. So this is carbon, 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 carbon. They have double bonds every other carbon, double bonds. And then they have single bonds to hydrogen. Let me just do the hydrogen in another color. Let me do it in magenta. Hydrogen. And obviously, the structural formula gives you the most information. Right? Then you can start to think about, gee, how will this interact with other things? While the molecular formula just tells you what's in the molecule, the empirical formula really gives you the least information. It just tells you the ratio of the different atoms in the molecule. Structural formula. Let's do a couple of more. Okay, what if we're dealing with, let's say we're dealing with water. I think you know the molecular formula for water, H2O. Now, what would be the empirical formula for this? Well, we want to know the ratio. So for every oxygen, there's 2 hydrogen, or I guess you could say for every hydrogen, there's a half of oxygen. So you really can't reduce this. If I wrote this as H2O1, what's the greatest common divisor of 2 and 1? Well, it's 1. So you just have to divide them by 1. So in this case, the empirical and the molecular formula are the exact same thing. It's H2O. What about sulfur? And sulfur is an interesting molecule, because obviously it's just one atom, sulfur. Sorry, not no, I'm spelling it wrong. No, I want to, it's not a PH, it's an F. Clearly I shouldn't be making spelling videos. So sulfur. Sulfur. So the molecular formula, S8. So it forms this neat kind of octagon-looking chain of sulfurs. That's what it really, and if I were to draw that, you would see that, and you could look it up on Wikipedia if you like. But it's empirical formula. If you had just a bag of sulfur, you don't know that each atom has 8 sulfurs. You just have a big bag of sulfur. So the empirical formula, there's only one atom in this molecule. You divide by 8 and you get S. So you just know that all you've got there is sulfur. So let's just do one more. Glucose. Glucose. Let me pick a new color. Glucose. The molecular formula is edit, undo, is C6H12O6. So for every carbon, there are, how many? For every 6 carbon, there's 12 hydrogen and 1 oxygen. So if you kind of reduce this formula to its empirical form, what do you get? Let's see, we can divide all of these numbers by 6. So we get 1 carbon, 2 hydrogens, and 1 oxygen. So this just tells you the ratio that they exist in a big bag of this molecule. This tells you the exact number of atoms in that molecule. Fair enough. So now we know a little bit of the difference between molecular formula, empirical formula, and structural formula. Now let's see if we can use this, what we know about the formulas and the periodic table, to think a little bit about the composition, the mass composition of some of these molecules. So the first thing to even think about is, how do you figure out the molecular mass? Right? So let me have my little periodic table down there. So molecular mass. Molecular mass. Or molecular, well, I don't want to say, let's say molecular mass. So the first question is, how do you figure out, I mean, the molecular mass is going to be the sum of all of the atoms in that molecule, right? So if you wanted to know the molecular mass of, let's say you wanted to know how much does one molecule of benzene mass. I don't want to say weigh, because it should be independent of what planet you're on. So what is the mass of one molecule of benzene? Well, all you do is you add up the masses of the different constituents. So you have 6 carbons and 6 hydrogens. So let's do benzene. So benzene. You have 6 carbons and 6 hydrogens. So what's the mass of each carbon? So let's go down to the periodic table. And just to give proper credit, I got this off of the Los Alamos National Laboratory's website. So let's see, the atomic mass of carbon. The reason why I use this one instead of my previous one is my previous periodic table that I got off of Wikipedia only had atomic numbers on them. But now that we're actually dealing with, we're going to start talking about the mass composition of different atoms or different molecules. We're going to have to start looking at the atomic mass, right? And remember, the atomic mass, when you think about it in atomic mass units, it's just the number of protons plus the number of neutrons. So you have 6 protons in carbon and roughly 6 neutrons. And why is there this decimal? Because we said before, this is an average of all of the masses of the isotopes that you'll find of carbon. So there's a little bit of carbon-14 on the planet, very little, but most of the carbon is carbon-12. When you proportionately average them, you get 12.01. But let's say we're dealing with, carbon-12, just because that's the most common element. So carbon has an atomic. Carbon is 12 atomic mass units. Right? And atomic mass units is a unit of mass, and we'll talk about how small it is. It's a very, 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 very small fraction of a gram or a kilogram, and we'll talk about that probably in the next video. So carbon is 12 atomic mass units. What about hydrogen? Let's see, go to our periodic table. Hydrogen's here in this dark blue, and I don't know if you can read it, but the atomic mass, this is interesting. The atomic number of hydrogen is 1. The atomic mass of hydrogen is 1.00008. So that tells us that most of the hydrogen on this planet has an atomic mass of 1. which tells us that it essentially has no neutrons. That hydrogen is a kind of an interesting nucleus there, where there's really just a proton sitting in that nucleus. And so if you were to ionize hydrogen, if you were to turn it into a cation and take one of its electrons away, what are you left with? You just have a proton. A proton sitting by itself, just a single proton, really is no different than a hydrogen ion. And that to me is kind of interesting, that hydrogen is that simple. It's really just a proton. So hydrogen has an atomic mass of 1, right? If it had any neutrons in it, it would have been at least an atomic mass of 2, but hydrogen has atomic mass of 1 atomic mass unit. So how much does one molecule, what is the mass of one molecule of benzene? Well, it's 6 times the carbon mass, so 6 times 12, plus 6 times the mass of hydrogen, plus 6 times 1. So that is 6 times 12 is 72, plus 6 times 1, plus 6 is equal to 78. Now, what if someone said, what percent of benzene is carbon? Well, then you say, okay, well, this is the piece that's carbon right here. The carbon piece of benzene is 72 atomic mass units. Right, that's carbon. So what percentage of benzene is carbon? It's 72 over 78. The whole thing is 78. So it's 72 over 78. And what does that equal? Let me get a calculator going. Let me get accessories. I should have had my calculator open ahead of time. Calculator. There you go. All right. So 72 divided by 78. 72 divided by 78 is equal to 92.3%. So benzene is 92.3% carbon by mass. And of course, the remainder, the 7.7%, is going to be hydrogen. Let's do that for a couple of these other guys down here. So let's say we wanted to know what is the mass of a molecule of water? Fair enough. Enough water on the planet. You want to know what that is. Well, we already know what the mass of a hydrogen is. It's 1, right? Hydrogen is 1. 1 atomic mass unit. Oxygen is what? Oxygen is 16. So notice it's exactly 16. So most of the planet, you have in an oxygen atom, you have 8 protons and exactly 8 neutrons. So you get atomic mass of 16. So oxygen has an atomic mass of 16 atomic mass units. So the atomic mass of the entire molecule, you have 2 hydrogens. So you have 2 times the mass of hydrogen plus 1 oxygen plus 16. So it equals 18 atomic mass units for water. And once again, if you want to say what percent by mass of water is oxygen? What's 16 out of the 18, right, is oxygen. So if we get the calculator back, you get 16 divided by 18 is water. So it's 88 let's say rounded, 88.9% water. 88.9% oxygen. So 88.9% oxygen. So most of water is oxygen. Even though, and this is interesting, even though you have 2 hydrogens here, and even though you have 2 hydrogens for every 1 oxygen, oxygen's mass is so much larger, it's 16 times larger, that most of water is oxygen. And now in the next, let me think. I'm probably running out of time. So in the next video, I'm going to talk about how do we go backwards. If someone gives you the composition, how can you get the empirical formula? And actually, on a side note, slightly unrelated to what I just talked about, I was doing some research last night about just about metals, because they're actually interesting about why some metals conduct more and some conduct less. And some sites, because when I first talked about, these were obviously the transition metals. They're backfilling their d orbitals, and I said, hey, the periodic table that was, I think I was looking in a Princeton Review book that described these as metals and described these as transition metals. And I was like, hey, well, that's kind of not fair, because I consider iron and copper and gold and silver to be as metallic as anything. Why should these be called, transition metals and these be just called regular metals? And it actually turns out that a common name for these are poor metals. Poor metals. Because to a large degree they're softer, they have lower melting points. So the intuition was right. To a large degree, these are, when we think of metals, these are these are the metals I think of. And when we think of metallic nature in a chemistry sense, we talked a lot about that. Who wants to donate their electrons the most? That's metallic nature. They're the guys down here. And then as you go to the top right, these want to donate their electrons the least. These are the most electronegative. They like electrons the most. So they actually have some of the worst metallic nature. So it actually makes sense to call them poor metals. Anyway, I just wanted you, and there's some debate on whether these should even be called poor metals. It's kind of, if you look up a bunch of periodic tables, some will call these metals, some will call these poor metals. But I just wanted to throw that out there just so you're exposed to it. And so for me, it is a little bit more intuitive to call these poor metals because they have less metallic nature than the stuff, especially down here, the alkali and the alkaline earth metals. Anyway, see you in the next video.